Hey guys. Profiling is one of those things that we all wind up having to do at some point in our career, but we don't tend to get taught how to do it in school. So this is going to be a fairly practical talk on how you actually get profiling into your workflow and how you actually use it, particularly for Python. So just for some background, what is a profiler? It's something that shows you where your code is spending its time. And more importantly, it's part of how you optimize your code in an intelligent fashion. And the intelligence is the important part there. How it works is basically you instrument the interpreter and then you run the code that you're going to run. Okay, so you run almost exactly what you want to run in production. And as you do that, you track the time that you enter and exit each function. And for the Python common profiler, C profiler, we also track how much time each function spends in every function that it calls. And what that allows us to do is to see where our function is spending its time. So the overall function spends a few seconds in this function, a few seconds in that function, and a few seconds in that function. And we do that for all of the functions in the application. Then we can build up a picture of where the whole application is spending its time. And the reason we profile in Python is because CPython is really, really slow. It is not a fast interpreter. It's not a very smart interpreter. And so obviously what we should do is we should just make CPython faster so none of us have to bother with any of this stuff. And that's what the PyPy project is basically doing. It's trying to build optimizations into the interpreter so that the interpreter will be able to make our high-level intelligent code run much faster. Now, the problem there, of course, is that's not an easy task. You're trying to optimize code in essentially an artificial intelligence style manner. You're trying to guess what it's supposed to be. Obviously, that's going to take some time and money. And the thing is, right now, computers aren't smart enough to restructure your entire code base to use better algorithms and the like. So even PyPy isn't going to save us from the need to profile. It'll just make it less common. So while eventually we're going to be using PyPy and it will make everything so much faster, today we still need to profile. And the other alternative would be to just optimize everything. And this is what my father's generation did. Every cycle mattered, every scrap of RAM really mattered, so everything they wrote was incredibly fast. It had to be tight, it had to be perfect. But the problem, of course, is that that code is very expensive in today's market. Computers are extremely cheap, so we may as well just use the computer and only care about what matters. So smart code is going to be the best thing you can do. If you have someone like my father who will just sit down and code every little scrap of code, well, you know, it's an amazingly fast system. Everything is perfectly gem-like. But of course, it's also not going to be something that your customers want to pay for. And that isn't really the problem with it. If you had the money, you could maybe do that. But the problem that makes it worthwhile to optimize in an intelligent manner is that optimization itself ruins the code that you're trying to maintain and extend. When you optimize something, you are introducing caches, you're introducing lazy loading, you're introducing parallelization, you're introducing assumptions that the system will work in a particular way, that, for instance, you'll be accessing a local file system versus a networked file system. And those assumptions and requirements get baked into your code. It makes it harder to maintain, harder to extend going forward. And when you start using low-level modules to optimize your code, when you start writing things in C, C++, assembly, CUDA, all of those optimizations tend to give your code more mass and keep it going the direction it's going. You can't pivot and go somewhere else. And when you get much smarter code, old ZOP infrastructure and the like, when you get something where metacode means that nothing that you've written is what's writing, something is intercepting everything and going off to the side and doing something else for you, you wind up with a case where, sure, it's fast, but it's extremely slow to write and it's extremely hard to maintain. And what we need is speed and maintainability. And so we pretty much have to give up, because there's no way we can ever become computer programmers. However, we can profile. And profiling is about that intelligence in the optimization. there's a generally accepted wisdom that only a tiny fraction of your code actually needs to be optimized. And Knuth basically said it's 97% of the time we don't need to worry about it, 3% of the time we really need to worry about it. And if we follow that, then we can isolate that pain, that weight, into the 3% that really matters. When we do that, our code can maintain the nice flexibility in the 97%, but the 3%, see which 3% we need to focus that pain into. And you might think, well, I really understand my code. Why don't I just say, well, obviously the problem's going to be in that particular algorithm that I know is going to be slow. The problem is, you really likely do not know which 3% it is. I've been coding for 31 years now, and I do not know what the problems are in my code most of the time. And you could be right. You could actually guess right, and many times you will. But again, fast code is very slow to write. It's an extremely expensive investment. And before you start doing that, you should be looking and saying, am I investing in the right thing? And that's what profiling is for. So how do you actually do it in Python? Well, this slide is basically all you need to know. Okay, there's a module called cprofiler. You can run it with Python -m cprofile. Give it the script you want to run, whatever arguments you want to run. And when your script is done, it'll dump out this nice, terrifying list of statistics. Each of the rows you're seeing there is one of the functions in your script. And you'll see there's a difference between the built-in functions and the Python-defined functions. And you'll also see things like string module. So the module itself is tracked as well. That's your initialization code and the like. In here, you can see the call counts on the left-hand side. Those tell you how many times each of these functions is called. When you get into larger profiles, you'll see things having 1 million calls, hundreds of thousands of calls. You can do a lot of analysis saying, this is something that shouldn't be called that much. The function identity is obviously that stuff over on the right. And something to note in this trace is time.sleep. Right? So this trace is actually sitting sleeping much of its time. And that's just because it's a test trace. So local time is the amount of time that you actually spend executing the code of a particular function. So the actual text within the function, this is what you're seeing when you see that second and third column. Graphically, the overall function has called these functions here. This little slice there is your local time. It's my runtime as opposed to the things that I've called. And that's mostly useful if you're looking to do spot optimization. And there are profilers that will actually let you look at the individual lines within the function. And we'll look at what those are later. So the next two columns are cumulative time and cumulative time divided by calls. This is what tells you the overall runtime. This is what is actually taking time. It's the whole box around it. It's time calling. So this is what lets you see what is actually taking all your time in a total sense. So, oops, sorry. So the first thing you're going to do when you start profiling is you're going to start fixing performance bugs, right? Quite often, we do not actually understand where the problems are in our code. So for instance, in this trace, there's a big blue box there saying, I'm spending all my time in time.sleep. Well, if I'm trying to get really fast frame rates, I probably don't want to be spending half my time sleeping and doing nothing whatsoever. So when we see these kind of things, when we see selects, when we see thread waits, what we're looking at is not a CPU-bound process, but probably an I/O-bound process, or potentially one which is sleeping and waiting. And that kind of profiling will tend to be timing-related issues. Those are things where you really shouldn't be waiting on a file loading while you're doing your GUI operation. So when we see way too many calls, that was that left column, when we see millions of calls to something, well, this may be an algorithmic issue. If you have something which is iterating over a large list, then iterating over another large list, and then calling something, you may have an issue that you need to deal with, which is algorithmic, which is like an ON squared analysis issue. If you see huge numbers, but it's actually valid, right? Like you've got millions and millions of data points, then you probably need to look at something lower level, which can process all of those data points at once. And as much as possible, you want to be focusing on the algorithms that you're using, right? When you're doing profile-driven optimization, if you can get an algorithmic fix, so do less work as opposed to doing the work faster, you'll find that it tends to be the best way to do it. If you can't do that, try to find an existing library which does the work that you're looking for. Python's extensibility means there are lots of libraries which can really help you optimize what's going on in your code. And only if that fails do you start pulling out your low-level tools, your C, your Python, C++. These are the kind of things that you want to hold as, oh, well, I'm stuck doing it, not something I pull out on the first moment I hit a problem. So in terms of how we actually go ahead and optimize our code while using profiling, I mean, we choose one of these approaches. We fix the algorithms, we code in a lower level language, the like. The question that comes up is, did you actually fix the performance, right? So we've looked at our profile, we've seen the problem, we've optimized it. And we're amazing coders, all of us. We know how to optimize things. And when you load up the big file, it feels faster, at least 2–3%, you can tell. The problem is, it is really easy to convince yourself something is faster when it's not actually faster. And so you want to be profiling your code at every stage, after every change you make when you're trying to optimize performance. And most importantly, you need to have a scripted test which does exactly the same thing each time. Otherwise, if you're relying on you clicking on a button or the choice of something that's over on a network, it's going to give you the wrong results. So when you're keeping these, I recommend that you only keep them for an optimization session, right? It might be a few weeks, it might be a few months. But generally speaking, you don't need to check these things into your source code controller, the like. Something to keep in mind, though, is over time, your profiler may not be giving you the same results. Profilers actually change, can run at a different rate. It has delays when it's doing the profiling. And so if your code is actually performance sensitive, it will often back off and run slower than it would in a normal run. It can also be affected by what else is running on your machine. So as you're working on your optimization, commit. And I tell you this, and you're not going to do it. But once you've been burned a few times, you'll start to do it. As you're working on the optimization, use real commit messages, right? Say, I altered this to do this, so that you can go back when it fails. Because it will fail, right? You're going to find that you try to optimize something, and all the machinery you introduced actually slowed down the thing you were trying to optimize. So 6 weeks creating a caching infrastructure that's going to solve all the world's problems, it's really hard to say, okay, I'm going to go back to where I was before. But try it. Really, it's the only way you're going to move forward. In terms of the tools we have, we've already looked at the standard profiler, cPro. Really good. It works pretty much every time you want to profile. You're probably going to look at cProfile first. It is deterministic, so it tracks everything, and it's very efficient. It creates very small files that you can load very easily. The flag -O lets you save the results to a file. And that's going to show up when we use the tools that actually visualize what's going on. We saw the cProfile results already. They're very nice. They're nicely formatted in that beautiful tape. It's really quite beautiful. I mentioned Line Profiler before. This is a tool that allows you to say, okay, I found the function that's causing the problem, but it turns out it's using a large amount of time to see which line is causing the problem. So to use it, you decorate a particular function with a decorator just called profile. You run the profiler, which is called kernprof, and the result is that it shows you the source code of the function and the amount of time spent on every single line in that function. And one of the things you're going to notice here is you see numbers that don't make sense, right? Like, so you're going 8, this one goes iterations. Well, why is that? Well, it's because it had to do one extra iteration to reach the end of the list. Timeit is a tool you use to determine which algorithm is better. Generally speaking, it's only really useful to settle arguments on Python list. It's not a particularly useful thing for general coding once you've already written something, but it will allow you to decide which algorithm you should be using if you can create a small enough test case for it. StatProf is a new profiling, but it doesn't tend to have a lot of advantages over using cprofile. It is slightly lighter weight. What it does is it interrupts the system all the time saying, hey, what's your stack, what's your stack, what's your stack, what's your stack, and sets up a statistical sampling instead of a sampling that's actually tracking when things enter and exit each function. This profile results, it has a few less columns, but it's basically the same result you get. Hotshot is another built-in profiler. This has been available since, I don't even know, like 5. It's deterministic and a tracing profiler. So this records absolutely everything that happens at runtime into this enormous data file. Unfortunately, there's very few tools which actually support Hotshot, give you any more data than using cprofile. So it's deprecated. Very few people want to use it. ColdShot is a replacement for Hotshot, which I'm writing. Basically the same model as Hotshot, but written with far more modern code. RunSnakeRun, which is one of the tools we're going to see in a moment. ColdShot, basically ColdShot minus O, whatever, run your script. Same basic idea as running cprofile. So at those tables of data. Tables of data are useful, they're nice and all, but it doesn't really make it easy to figure out what's going on. So a long, long time ago in the Pleistocene era, a tool was created called kcachegrind. And it's primarily for C programmers, C++ programmers, but it has some importers that allow you to see what a Python script is doing. So same basic idea, you run cprofile on something, you run a little converter script, and it will pop up kcachegrind. So this is what kcachegrind looks like. You've got that same kind of graph that we've seen before. You've got the outer thing, which calls the inner thing, which calls the inner thing, and this little series of things that get called in there. It has a call tree view as well, so you can see a big long graph of what called what. RunSnakeRun is basically a Python-only version of kcachegrind. It's much newer. It's, again, one of the traces, as well as memory profile traces. RunSnakeRun basically runs Snake on one of those profile files you've saved with the -o command, and it pops up like this. So as you can see, very similar. Because it's Python-specific, it's loaded into RunSnake instead of in kcachegrind. It does a better job of assigning what called what, so you can actually see what's going on. gprof2dot is an older tool. It creates dot, which is a graph format files. Generally speaking, people who actually use it script this up so that they just run their profile and immediately up pops the result. Don't trying to memorize all that stuff. What it does is it creates this huge graph of what called what, and it uses color coding. So the red says that's incredibly hot, less hot, and this stuff's cold. It doesn't really do much. So if you have a large enough monitor, you can view that and see everything that's going on and see a nice trace of what's viewing it. New project, kind of a replacement for RunSnakeRun. It's a web-based version of RunSnakeRun, basically. And SnakeViz, mechanism for using it. You run the profile, you run SnakeViz on that output file you saved, and this is what it looks like. SnakeViz is very new. It still can't handle it. It took me quite a while to create a profile that was small enough for it to load. So one of the things we're probably going to do this sprint is try and make it much faster so that it can load so do come out to the tool sprint. It would be nice to have lots of people working on making tools that are better for people. Anyway, so in terms of getting your code profiled, all of these things where we run it at the command line are fine, but quite often we don't want to profile our whole application, right? Because profiling introduces delays. It makes it harder to figure out what's going on. So all of the major profilers have the ability to use a decorator where you say, just profile this function, right? And there's also middleware and things where you can say, okay, I just want to profile this request coming in, right? So in Django, if you just want to profile that one view, you can decorate just that view. If you only want to profile a view on some condition, you can actually write just a piece of code that says, if whatever, start the profiler and stop the profiler when you're done. Other things that tend to cause problems are C main loops. particularly when you're trying to profile GUI code, PyQt, they tend to have a problem in that they never actually come back to the Python code after they're done. ColdShot does handle that, so if you need to, you can use that. For profiling websites, as I mentioned, there's WSGI install into your Django, TurboGears, etc. stacks, and just profile every request that comes in, or you can use those profile decorators. One of the things that we still haven't solved is things that look like functions but actually aren't tend not to show up in profile traces. So things like C-types calls, Objective-C calls, they tend to just not show up at all. NumPy operations like slicing and the like also don't show up. Profiling PyPy you would expect to be the most difficult thing in the world. The only major change here is you have to profile instead of C profile. Use profile in Python 2, it's not usable. What won't work with the Python 3.1 is any of the tools, though. The tools all use the Python library to load, and none of the tools have been ported over to Python 3 at fixing during the sprint. How am I doing for time anyway? Oh, fine. Interesting hotspots that you're going to find. The whole point here is to catch problems in code or fix things. If we look at caching, it's one of the most common things we do. We trade off space for time. And it's one of those things that, generally speaking, you're in school, the teacher says, yeah, use caching whenever it is. But caches actually cause a lot of problems. Oh, sorry. They're one of those things where if you are not using your cache correctly, it will quite often cause more problems than you're solving with it. Really, things like not storing the value in the cache that you intended to store in the cache. Invalidating caches by storing values in them, that kind of thing. Other issues that come up, when you violate the abstraction that you're using, ORMs are one of the common ones, you iterate over each record, pulling out another record. Each one of those records you're pulling off on the side creates another request. Common issues in modules, logging in particular, sucks. It's really, really bad for performance. It's a great module, but it's really bad for performance. And the warnings module, which uses it, is the same basic code. Silent discards, this is something that just you look at it and go, dude, what was I doing? If you're loading up a gigabyte to check a byte and then read what the library assumes can be done. The library's been optimized for something, and you're breaking it. ORMs in particular, they'll spend an enormous amount of time looking at what's going on, building internal caches of what's supposed to happen. And if you use it in a short-running process, you'll be dead. Or, well, you'll be slow. Memory behavior, something that it doesn't feel like you should have to worry about in Python. Python users should never have to deal with memory, but particularly things like temp objects, if you get up to millions and millions of operations a second, even just creating a little list or a little dictionary to store the values that you're going to return can actually start to add up. Again, profile first. If that's your problem that you're going to call in another function, you can intern it by making it an argument. And don't do that unless you're trying to win a contest or an obfuscated Python code. Never do that, okay? It's not a good idea for many reasons. Properties, you're going to find this if you do a lot of property operations onto the network or the like. There are going to be libraries that you pass those objects to that are just going to blow up because they assume that everything is running fast. Encode and decode, this is just something where you shouldn't. If you're doing networking code, particularly low-level binary networking code with lots of bit offsets and the like, in Python, your code is just going to suck and you should really stop. C code in Python, that's that same idea. You get that textbook that says, well, here's the little algorithm, shift bit A onto bit B, do a rotation on whatever. Do not do that code in Python. Really, it's just not worth the pain. Python is not good. One that Guido likes to point out to people that you should use less functions. Don't, actually. My advice would be, if you are getting to the point, something else to optimize yourself. And so, moving forward in profiling, where we're going to be moving forward, I'd like to be working on tools this sprint, RunSnakeRun and maybe SnakeViz. ColdShot, because it's a tracing profiler, should be able to do a lot more interesting stuff. For instance, being able to go into an individual call and say, this is how much that individual call took, and break it down into more nuanced views of it. So that's all I have. I'm hoping there are questions, because I think I've got, 13 minutes left. So, yeah, oh. So, no questions? Okay. Well, then I get to do this. Oh. Okay. So, this is what RunSnakeRun looks like. Okay, so this is an extremely simple profile. You can see there that I've basically got a number of operations going on. In this case, it's just import this, all right? And a PyCon thing 15 years ago or whatever it is now. It does incredibly stupid things to obfuscate the fact that it's got Tim Peters' little quote in it. So we go into it, we say the module said, okay, I'm going to do an import. The module this takes almost 0.03, or 3 milliseconds to run, and it does 856 calls to dict get, which makes no sense whatsoever. And then it goes ahead and does another 104 calls to CHR, and another, I don't even know how many it does. Well, 1 call to join. So it doesn't make any sense whatsoever. But this is actually one of the things you'll occasionally do with profiling. You'll pull up an application you don't know in get operations and the like, and you can say, okay, well, I want to focus on what that thing is. To give you an idea what a real one looks like. Oh, actually, no, sorry. We'll do another quick sample, because everyone should be using. So this is what requests looks like. If you just run requests.get, you see, you can see what it's doing, right? Right down here, way at the very bottom, it does a receive on a socket, right? And all those levels of abstraction come down to say, okay, well, that's where we will receive some data from a socket. And we can go to each of these and say, okay, well, that function is actually send. This function here is content on something. And because we've got the data here, we can say, okay, well, it's sitting in models.py inside requests. Okay, so I want to know what to do. I'm going to go into models.py. And if for some reason we thought that it was receiving too slowly, I mean, in this case, it's requests. It's working pretty well. But we go down into receive and say, okay, well, I'm going to figure out how to optimize this function right here. One thing that we can also do is we can do a view that shows us which packages are currently, or which packages are involved in this operation. So this view is broken down by which package and which module the code is in that the time is being taken in. So in this case, I believe that's, what is that? That's request.py, that's low-level code. So what is this here? Okay, so unfortunately, request doesn't actually use a lot of libraries because it's just built-ins. But what we can do here is we can say, okay, my code is actually limited because I'm using that's actually spending all the time for me. Any questions come up yet? No questions yet. Okay, well, then we will pull up something a little more interesting. So here's a realistic profile, and it's one we've seen before. But this is a 3D renderer in Python. I don't know if I can actually run it on here. Let's see. Oh, no, I can't. Okay, so if you look at it, you can see that it's spending most of its time over in, whoops. You can spend most of its time over rendering a teapot. Okay, so rendering a teapot should not take anything like that long. Teapots are really simple to render because they're low-level operations. Everyone knows 3D graphics is, teapots is what you render. Well, it's true. That's what you do. So the thing about it is that teapot should not be taking so long. So if I wanted to optimize this, which honestly I don't because I don't really care about teapots all that much, but if I did, I would look at that particular piece of code and I would say, okay, well, where is this thing defined, right? And I can go in here and I can say, okay, well, teapot.py is actually defined over in, and you know what? On the small screen, it's really hard to use, but it's way over here in this little line here. So we can actually go in and say, okay, teapot is over in OpenGL context somewhere. So we find OpenGL context, open up that file, start optimizing that particular function. What else can we do with this that's fun? We can go into, when we go into the file view, we can actually see, okay, this here, where is it? Yeah, so that's the actual module that I'm running. That's the code local to that module. And as you can see, a significant portion of the time that I'm running is actually just importing and setting up the module. Now, there are actually profilers available. Line Profiler has a profiler that will tell you what the imports, like what took time during importing. Basically, this is all time importing that module. So most of my runtime is just importing the module. The reason that happens, all of OpenGL, which does an enormous amount of work setting up hundreds of thousands, well, it's not hundreds of thousands, it's I think a couple of thousand entry points in C types, which takes rather a lot of time. Any questions yet? A question. I can stop blathering. Almost nothing. They probably run pi to 3 or 2 to 3 across it, and it should pretty much be ready to go. The only real issue is that because they're running in a different version of Python, the loaders are dependent on the Python version. So they just have to run in Python themselves. RunSnakeRun will be a little bit more complex because you have to port WX-Python, well, you have to get WX-Python built for Python 3 first. SnakeViz should be trivial. It's using all portable libraries, they just have to be ported. gprof to dot should be trivial again. It's just a low-level library that loads something up and dumps it out. So most of the tools should be portable fairly straightforwardly. There is a port of WX-Python to Python 3. It's just not widely available, so in theory, someday soon, it should be portable. The code itself needs to have 2 to 3 like stuff run over it, but it basically should work.
So does RunSnakeRun actually run the code, or is it just for analyzing the dumps?
It just looks at what's going on. Yeah. So.
Thanks. This is really cool, by the way. You mentioned earlier, one of the problems that I've always faced with large Python applications is where you can't just say profile the whole thing because it takes forever to run and the performance really slows down quite a bit. So one of the things for monkey patching library for profiling. So it's called, there's one called TAC, which is on GitHub, and there's another one that I've been working on called Scrutinize. So what you can do is you can take a large program that normally you can't, you mentioned decorators and things for getting in there, but this allows you to do it non-invasively. So you can just point at whichever functions you want to do and then call out to cprofile or whatever externally without having to affect the underlying code. So we should talk afterwards. That's very neat.
Sounds good. Okay. So apparently you don't need to alter your code. Anyone else? No? Okay, I think we're getting pretty close to time on it. Oh, okay.
We can take one more question if
okay.
he seems to be
no. Okay.
something into the mic.
Oh, could be.
Sorry, trying to find my way around.
Okay.
First of all, cprofile is freaking awesome.
It is, yeah.
Yeah, I was just running it through some of my code and having trouble interpreting some of the results. So I was wondering if I could kind of sort of put you on the spot and ask you to help me later.
Sure, okay. Well, if you're having problems, what's the question? And then we'll find out.
Here's the thing. It means one of two things. Either I'm doing something wrong or I'm writing code more efficiently than I thought I could.
Well, it very much depends on what you're doing. If it's evaluating to 0, 0, the timer frequency is approximately 1 in a million, and it displays it at 1 in 1/1000th of a second. So it'll show up, but it'll show up way off in the margins. Now, if your code really isn't efficient, it may just be failing. Like, it may just not be able to pick up what your code's doing, and that's probably where you'd use hotshot or coldshot. The difference between them is hotshot and coldshot do almost no work at runtime. They just say, okay, dump everything that comes in out to disk. And As a result, they introduce very little variance in the code, right? Like they literally say, these are the 3 values, dump those 3 values out. These are the 3 values, dump those 3 values out. And what that tends to do is you get a very nice, precise view of what's going on. With the C profile, what it's actually doing is it's doing a lot of bookkeeping internally, which is trying to compress out those stats so that it can save a very small file. And the result of that is like it can basically swamp what you're doing, and internally it has a heuristic where it says, I'm going to subtract this much from each call for how much I'm using. And there are actually very low-level things inside C profile where you can say, go try and calibrate yourself again, because you seem to be running off. Mm-hmm. So basically, it's most likely just a problem with C profile just being a little bit too conservative. Cold Shot, for instance, does absolutely none of that. It records things like, absolutely, this is the time you started, this is the time you stopped. And there's no way for it to get down to a 0. Right? Like it can't get down to a 0, except if you're switching between different processors on a machine. In those cases, time can actually go backwards. Well, because the synchronization of cores on your CPU, the operating system tries to keep them in sync, but they can actually, like time can go backwards when your process switches from here to here. So again, that's that. Although in theory they're deterministic and it should never cause a problem, if you're getting down to that kind of level, you're probably fast enough. Right? Like if you're getting down to a level
awesome.
where that,
I actually can write really fast code then. Thank you.
There you go. Okay. Okay. So, thank you very much, guys.